if you remember back in the von Mises system, this 1/3 stuff over here is your shear component. Alright? In other words, this one from your diagram. Okay, this thing over here. Okay? It's equals to your square root 2/3 of your U strength. Okay, then we rearrange and we prove that this is the one that we've been keep using. This equation is the same equation that we have been keep using for like the past stuff, right? In solving other stuff, which is this one. Okay, your U strength or your von Mises stress, so to speak. All right. So therefore, if you were to do this, then and get the stress invariance of this thing over here. Alright, I don't know how do you get the stress invariance, but that's how they return this thing over here. Okay, some magic appears and they rewrite this, and they assume S3 is equals to 0 for your general equations over here. So these are all zeros. This is 0. Alright, to simplify things and things like that. And therefore you have some equations over here. You sub in your invariance, which is all this stuff. I don't know how you sub in. By the end, you plot something like this. Okay, you plot something like this, and this is the von Mises curve. Okay, for maximum principal stress criterion, alright, we haven't discussed, but I'll just talk to you now. Is that if you still remember, there is stress 1, stress 2, stress 3, right? If you go to 2D, something like this. So your stress 1 must be greater than your tensile in order to so-called break it apart. You will not yield, but you'll break it apart. So this is somewhat a good prediction for brittle materials, or you may yield a bit, things like that. Alright, so maximum is talking about the normal stresses. Alright, not perpendicular to the planes. If you sigma 1 and then sigma 2, things like that. Alright. Later on we'll talk about how do we use this thing when we combine everything together. Right, so this is just basically for the maximum principal stress criterion. It's simply talking about normal stresses, or the U stress that we're talking about. Just purely the U strength, but I think it's the ultimate strength. The ultimate strength that reflects this point over here. Alright, so instead of this point, that is our U stress, talking about this point, it straight away break. Alright, so the maximum principal stress deals with that. Okay, and then if it's for a Tresca, then the shape is something like this. Okay, later on we'll talk about it. And for von Mises, we actually show you briefly. Looks like this. Okay, and therefore if you to combine everything all together, you have this thing over here. Although Tresca versus von Mises also versus maximum stress. Right, so it's a comparison between all this stuff together: maximum, Tresca, and von Mises. Right, so how do you use this thing to predict a certain material? You can see we are assuming in terms of 2D. Alright, sigma 1 and sigma 2 only. Okay, repeat, how do you plot this graph is simply dealing with some invariance. Alright, and we don't know how to derive, and therefore we come here. Alright, at least you need to know for some reason, maybe in the future you need it and things like that. Alright, when you have stress 1, maybe I should write this as 0.5, maybe this is 0.5. Okay, so if you have input maybe a certain 0.7 stress 1, so stress 1 is equals to 0.7, or stress 2 is equals to 0.25. Okay, stress 2 is equals to 0.25, then we're talking about a point over here. So when you subject a certain material with this particular stress, with stress 1 and stress 2, stress 1 and stress 2, alright, you have a certain movement in this diagram. Alright, and this movement is being plotted over here, and this result is, or the stress state is being plotted over here. Okay, and this pooling of the stress 1 and stress 2 on this axis will actually initiate a so-called tensile to this material. Alright, this simply means that it's plane 1. Alright, and this is plane 2, this is plane 3, this is plane 4. So for each of the plane where you apply a different forces, where you have a certain stress 1 in the negative stress 1 direction, you're actually compressing it in the in this zone. If you were to pull in the positive direction, you're talking about tensile. If you compress it, it's talking about negative sigma 1. Alright, same thing, if you're talking about a compressive negative 2 or negative sigma 2, which is over this side, as you can see, this is negative 0.5, which is in the sigma 2 direction. Minus sigma 2 direction. Maybe I should write minus sigma 2 and minus sigma 1. As you can see, that minus sigma 2 is compressing, and that minus sigma 1, alright, minus sigma 1 is also compressing, and therefore the whole thing is to be compressed. Things like that. Alright. Instead of sigma 2 only, you can actually divide by the yield strength of the material, or the yield the critical the critical stress of your material, or the yield stress of your material lah. Alright, so you have a ratio of 1, because when you reach when your sigma 2 reaches your yield stress, then it's equals to 1, because sigma 2 over sigma y is equals to 1. Alright, so when you reach this means that you're at the max normal, which is the 1. So they're all 1s over here now. Alright, if stress 2 exceeds, then you have 1.5, something like that. For example, 15 divided by 10, you have 1.5. It's 10 over 10, and it's just simply equals to 1. Alright, for different plotting, different ratios of the stress input, you have a different stress state. Alright, showing that you are safe over here, or you may be safe over here, and things like that. Alright, and these are all the materials being used. Alright, fracture lah, or maybe yielding. Okay, so the more brittle you are, the more fixed shape that you have over here. So the more ductile you have a slightly curvature like this, and more curvature like this, things like that. That's what I will foresee lah. I may be wrong over here. As long as your difference is less than about 15 to 10%, you should be safe. Right, for Tresca or Von Mises. Right, so they are equally applicable for ductile materials. Alright, metals I mean. The Tresca is more conservative because you will have a less allowance. Alright, as you can see, the Von Mises is somewhat with somewhat more tolerance than your Tresca. So Von Mises can actually take in more stuff before it fails, something of that meaning, right? And things like that. Summary, if you still remember, this one is your SY, this one is your KY. Alright, this is for your Von Mises, if you still remember in the Von Mises video. And then we derive all this stuff, but I didn't actually see that they actually derived over here. But anyway, then if you were to compare the Von Mises, alright, so the Von Mises step is actually taking this step, J2 minus your KY square, we have proved to you, right? So in terms of Tresca, the function is in terms of the average shear stress minus away your shear stress of your yield stress, or your shear component, or the deviatoric system, if you still remember all the way back. Alright, the deviatoric system over here. Alright, so you have a certain stress state. Alright, and then you minus away your hydrostatic stress. In our case, we call the hydrostatic stress as your yield strength of the material, which is normal to the plane. Alright, but since we know that the normal to the plane, the yield strength doesn't actually cause yielding, which is also which in fact is the shear part, the shearing part, since the hydrostatics are all gone already, or the principal stress are all 0, and therefore the pure shearing or the pure plasticity deform is talking about the shear component of your yield strength, so to speak. Alright, just briefly take note of it. Alright, and therefore in terms of Tresca, it's something like this. Alright, this is your SY, this one is your KY. So if you were to compare Von Mises and Tresca, is somewhat of that meaning over here, as you can see. Alright, this is times 2, this is times square root 3. Alright, you can see it's a difference between your principal stress, your your hydrostatic stress for some reason, equals to the multiplication to your so-called the shear part of your yield stress, so to speak. Alright, for this ends the criterion. Alright, the plasticity criterion. If you lie anything outside this zone, you are considered unsafe. If you lie anything within this zone, you are considered safe. And safe and unsafe talks about your criteria to be safe or unsafe, things like that. and therefore this is the end. And therefore let's talk about other stuff in the next video. See you there.